Sulfur. Why is it a non-metal, not a metal? First thing is iron sulfide. Sulfide is acting as the anion because sulfur is non-metal. So first chemical property is that sulfur forms anions in ionic compounds. Forms anions in ionic compounds. Second, sulfur is going to form an oxide, sulfur oxide. And the sulfur oxide is going to be acidic because if we dissolve sulfur oxide in water, we're going to produce sulfurous acid or sulfuric acid. What are we talking about? We're talking about the acid-base chemical properties of oxides of period 3. Oxide, sulfur oxide forms acidic. Sulfur oxide is acidic. Sulfur oxide is acidic. Back to the bonding nature of ionic sulfide. Like all the other bondings, the nature is going to be electrostatic attraction. Electrostatic attraction between Fe2 plus and S2 minus. Fe2 plus, S2 minus, cation and an anion. And that is because there has been a transfer of 2 electrons from the metal ion to the non-metal sulfur. Electrostatic attraction is the nature of ionic bonding. Between a cation and anion as a result of electron transfer from metal to non-metal. Great. Let's look at the anion sulfide ion. Electron configuration. Not condensed, but full. So that we need to start from all the way from 1s. Starting with 1s, 2, 2s2, 2p6. Now let's be careful. 3s2, yes, but 3p what? Well, it's going to be 6 for sulfur, but we're dealing with sulfide ion. So for sulfur atom, there should be 3s2, 3p4, but for sulfide ion, it should be 3s2, 3p6. Sorry about that. Ionic radius, comparing sulfide with oxide ion. Oxide ion comes from oxygen, which is in the same group, 16, with sulfur. So we know that down the group, there will be increase in ionic radius, and that is simply because there are more electron shells. Specifically speaking, sulfur is right below oxygen, meaning there is one more electron shell. Sulfide has one more electron shell, principal energy level, than O2 minus ion. Classify bonding into 3 types: ionic, covalent, versus metallic. Well, different substances have different bonding nature. All of them are electrostatic attraction nature, but between what and what is different. Ionic, cation and anion. Covalent, shared pair of electrons and the surrounding nuclei of the bonding atoms. Metallic, between lattice of metallic cations and the surrounding sea of delocalized electrons. So different compounds have different bonding nature, and they also will therefore have different properties. So we're able to explain properties of different compounds and substances. Explain properties of different compounds and substances. We're going to be extracting iron from iron sulfide. And the first step is to form iron oxide and sulfur dioxide. Okay, iron sulfide is going to combust, in other words, react with oxygen, which will produce iron oxide and sulfur dioxide. Let's write the equation. So let's write the reactant as iron sulfide, FeS, it's going to be solid, react with gaseous oxygen, which will produce iron oxide. But look at the Roman numeral 3, IUPAC nomenclature for iron oxide, where iron, transition metal, can have variable oxidation states. We will have to acknowledge how iron 3 will combine with oxygen in the ratio of 2 to 3. Fe2O3 means 3 plus Fe, 2 of them will bond in a balanced way with 3 oxygens. Again, Fe2O3 will be solid, but sulfur dioxide produced will be gaseous. We know what the reactants and the products are. All we have to do is make sure the number of constituent elements of the reactant and product molecules are the same left and right, reactant side and product side. Starting with the reactant, we'll have to have 2 FeS to produce 1 Fe2O3. We'll have to end up with 2 sulfur dioxide if we start with 2 FeS. On the product side, overall, we seem to have 3 plus 4, 7 oxygen atoms, which means we'll have to start with 3.5 oxygen molecule. 3.5. That's a 3. Let's make sure what we have written are nicely balanced. 2 FeS plus 3.5 oxygen will give 1 Fe2O3 and 2 SO2. Right, completely balanced. Moving on. We have change in oxidation state of sulfur. Yes, we do. Sulfur in the reactant side is an anion with -2 oxidation state, which will turn into SO2. This is a simple covalent molecule compared to the ionic compound of the reactant FeS. Sulfur has bonded with another non-metal oxygen to form simple covalent, in which sulfur is less electronegative than oxygen, therefore will have positive oxidation state. In this case, +4. -2, 2 plus 4, that's clearly oxidation. Production of sulfur dioxide will cause some harms to environments. Environmental concern primarily being about how sulfur dioxide can be the cause of acid rain. SO2 dissolving in water to produce sulfuric acid. So acid rain is the process that might raise environmental concerns. If we add carbon to iron, what we're doing is introducing carbon atoms to pure iron so that the iron metal is no longer pure. It's alloyed with carbon. There are advantages, mostly, which is that it's harder. It's harder for a reason, and that is, the idea is that because the lattice of metal ions are of irregular size, so iron is going to be bigger than carbon, which means that the irregular layer of metal ions means that when the alloy substance is hit with some force that leads to breakage, well, the layers need to break by sliding. But then if the layer is of unsmooth, different sized ions, the layer sliding will be not as easy. So layers will not slide as well, which means the metals will not break or mold as well. So alloy, the carbon and ionic lattice is of irregular size. The regular arrangement of our metal is disrupted, which means that the layers will not be sliding over. Will not slide over each other as well. First question is done. Now ready for us to move to the second question. About this time, hydrogen sulfide. Again, sulfur is involved here. This time, sulfide is going to be in a simple covalent structure with two hydrogens, very similar to oxygen, which would look like a bent shape. And we are asked to draw the Lewis structure of hydrogen sulfide, which will look as follow, but then because Lewis structure requires us to draw presence of lone pairs, sulfur does have lone pairs, not just one, but two. We have our Lewis structure. The shape of hydrogen sulfide molecule is going to be bent. Remember, we've got 4 electron domains, out of which we've got 2 bonding pairs, 2 lone pairs, meaning we'll have a 104.5 degree bond angle called bent shape. And obviously, we may also call this shape, this molecular geometry, as free-shaped. Hydrogen sulfide can act as an acid. That's understandable. Why? Because we have hydrogens which can dissociate as protons and give away of protons is what acids do. Which means if H2S deprotonates to H plus and HS minus, we will call HS minus the conjugate base, the product of acid dissociation. HS minus is the formula of H2S conjugate base, and we are asked to identify whether H2S is strong or weak acid. In other words, how well does H2S dissociate? Does H2S completely dissociate or only partially dissociate? How are we able to determine this? From the concentration value we are given as well as the pH. This is how we identify. Initially, we have 0.1 mole dm cube minus cube of H2S. If the acid was strong, then we would end up with 0.1 mole dm cube minus cube of H plus, which doesn't seem to be the case, but only 10 to minus 4 mole dm minus cube. H plus concentration is 10 to minus 4 as we are given from the pH value. What do we know about H plus value? 10 to minus pH. So we know that H2S is going to be a weak acid because only partially dissociates. If we are to calculate the hydroxide ion concentration, we need to think about the relationship between H plus and OH minus with the assumption that we're dealing with room temperature. pH plus pOH equals to a number, and this number is specifically 14 with the assumption that we are in room temperature. We need to utilize this equation, which can also be represented in other forms, H plus times OH minus. Concentration is 10 to minus 14. Both derive from the same concept of ionic product of water. The idea is that our pOH will be able to give us the OH minus concentration, and we can work out pOH by 14 minus pH, which is 4, as we're told in the preceding question. pOH being 10, OH minus concentration will have to be 10 to minus pOH, which is 10 to minus 10 mole dm minus cube. Nitrogen and hydrogen sulfide mixture is going to react with sodium hydroxide, and we're given the volume of the mixture pre and after the reaction. Seems that 25 cm cube has been consumed, which means 25 cm cube of hydrogen sulfide was the volume of hydrogen sulfide in the initial mixture. And we're given the task to work out the mole percentage of hydrogen sulfide. Okay, so what we need to do is work out the mole of hydrogen sulfide and divide that by the mole of the gas present in 550 cm cube. So we need to use what equation? We need to use the equation of N equals volume of gas over 22.7 dm cube per mole equation. So if we put in 25 cm cube, which needs to be converted into 0.025 dm cube, we will be able to work out the mole of hydrogen sulfide present, which we will divide by the volume of the total mixture, which would be 0.55 dm cube over 22.7 dm cube per mole. This fraction is going to be the percentage. It will give us the fraction of hydrogen sulfide within the mixture which can be simplified as 0.025 over 0.55. And if we times that by 100, that will give us the percentage, which will be 4.5%. The assumption we're making is that both gases, nitrogen and hydrogen sulfide, both nitrogen and hydrogen sulfide act as ideal gases. Moving on to question 3. We are again dealing with iron, Fe related ionic compound, iron ore, Fe3O4. And this time there are 2 ions involved, Fe2 plus and 3 plus. Fe3O4 ore has both of the 2 plus and 3 plus ions, and we have to work out their ratio. Right, how do we work this out? Well, we have to look at how much do the anions contribute to the ionic compound, and that would be -8 from 4 oxygens, which means +8 has to come from 3 ions. And it cannot be done by just Fe2 plus or just Fe3 plus. It will have to be a combination of the 2. Well, I can see how 2 Fe3 plus and 1 Fe2 plus will contribute +8. So let's go with 2 Fe3 plus and 1 Fe2 plus. State the type of spectroscopy that could be used to determine their relative abundances. Relative abundances of isotopes can be indicated by mass spec. Mass spec will tell us about the relative abundances of isotopes. The other spectroscopy, IR, infrared, and 1H NMR, are for bond vibrations, IR, and hydrogen environments for NMR. Okay, let's work out the number of protons, neutrons, and electrons. We will be looking at the mass number 54 and the atomic number 26. The atomic number represents what? Number of protons, which will be equal to the number of electrons in atomic state. Obviously different in ionic state. 26 will be also for the number of electrons. And the number of neutrons will have to be the mass number minus atomic number, which would be 28. Moving on to the ionic form, 3 plus ionic form of the isotope, the bigger isotope. We have mass number 56, atomic number 26. Number of protons will equally be 26, but the number of electrons will not be 26 because we have 3 plus charge. We've got 3 electrons less. Hence the 3 plus charge, meaning number of electrons will be 23. Neutrons will be, this time, 2 more to make a bigger atomic mass, 56, so 30 in total. Iron has specific heat capacity. We're going to find the specific heat capacity. Calorimetry calculation question. So what's the equation we have to use? We'll have to use Q equals mc delta T, where we're given the Q value, which is going to be 1,000 joules. Make sure we use 1,000 joules instead of 1 kilojoules, because specific heat capacity is in joules per gram per Kelvin. 1,000 joules is going to equal to 50 grams times 44.4 Kelvin, and our specific heat capacity, which will equal to 1,000 joules times 50, no, sorry, not times, over 1,000 joules over 50 grams and 44.4 Kelvin. Do the math, will be given 0.45. Let's put the units in, joules per grams per Kelvin. Balancing the oxidation half equation, easy. All you have to do is add an electron or two, or even sometimes three on the product side. Reduction, not so simple. Not only will we have to add electrons, but also water to match the number of oxygens, and H plus to match the number of hydrogens. In this case, we are going to look at an unusual case of hydrogen peroxide to water, which would look H2O2 turning into H2O. And from here, we're going to start by matching the number of oxygens by saying that 2 water will be produced from reduction of 1 molecule of hydrogen peroxide. What's the second step? The second step is to match the number of hydrogens. Now, how many hydrogens do we need to add to the reactant side? 2. So that we have 4 hydrogens in total on both reactant and product side. What's the final step we need to do to balance, to complete the reduction half equation? That is to make sure the number of charges on the left and on the right are equal. Currently, we have 2 plus charge on the reactant side and 0 neutral charge on the product side. How can we remove the positive charge on the reactant side? Well, let's rethink about the purpose of this reaction. The purpose of this reaction is to reduce hydrogen peroxide. And how do we reduce hydrogen peroxide? Well, we're going to add electrons. And we're going to add 2 electrons to make sure 2 positives are neutralized by 2 electrons. Also, let's make sure we add the state symbols. We're going to make sure hydrogen peroxide is in aqueous state to become liquid state of water. Next up is going to be balancing the 2 oxidation and reduction half equations together to a complete balanced redox equation. How do we do that? Well, we're going to have the oxidation and reduction half equations up and down each other, so that we have something like this. I'm going to bring down the oxidation half equation below the reduction. From here, I'm going to make sure when we simultaneously add the 2 half equations, the electron species are cancelled out. Therefore, I'm going to multiply, I'm going to double the oxidation half equations all by 2, so that we will have cancellation of the 2 electrons, so that when we have the product of the 2 half equations simultaneously added, we will end up with 2Fe2 plus and hydrogen peroxide in acidic environment will turn into oxidized iron and to water. Add the state symbols, we will have the following: hydrogen peroxide plus methane and oxygen will give methanol. The reaction can occur below 50 degrees Celsius if gold nanoparticle catalyst is used. Well, this question is about Maxwell-Boltzmann kinetics. Firstly, we will look at uncatalyzed reaction, which means we will look at the effect of increased or decreased temperature. And all right, we're given the task to draw another distribution curve to what is already on the graph at a lower temperature. Okay. At a lower temperature, more of the molecules will have lower energy, and less molecules will have high energy, which can be represented as a curve that is skewed to the left and also higher towards the left and lower towards the right, which represents how only this much, indicated by the small area, small shaded area under the curve, will successfully react compared to this much, represented by the red shaded area for higher temperature. We're also asked to indicate the effect of adding a catalyst. Well, the role of catalyst is to lower the activation energy by providing an alternative pathway, which means the activation energy uncatalyzed will be reduced when it's catalyzed. Hydrogen peroxide could cause further oxidation of methanol to methanol and methanoic acid. So oxidation is going to produce methanol, but further oxidation will produce methanoic acid. Methanol is usually manufactured from methane in two-stage process, two-step reaction, which can be merged into a single reaction equation by removing what? The intermediates. Who are the intermediates? I can see how carbon monoxide is an intermediate, as well as two hydrogens. Specifically speaking, there will be one hydrogen remaining at the product site, meaning we will be starting with the reactants methane and water only, giving our methanol and single hydrogen. If certain amount, 8 grams of methane reacts, how much hydrogen do we produce? Stoichiometry question. So what we need to first look at is in what molar ratio does methane convert to hydrogen? 1-to-1 ratio. 1 mole of methane will produce 1 mole of hydrogen. So if we know the mole of methane inputted, which can be calculated as M over big M equals N, where the small m, 8 grams, over the molar mass of methane. Methane has the molar mass of 12.01 plus 4 times 1.01, which in total will give grams per mole, which is the unit for molar mass. Do the math, and we'll be given the value for number of moles of methane, which will also equal to the mole of hydrogen. Now that's the point. And for working out the volume of hydrogen, well, we need to use the equation N equals volume over 22.7 dm cube per mole. So what we need to do is multiply N of H2 by 22.7 dm cube per mole to work out the volume of H2 in dm cube. Are we given specific request for the unit of volume? dm cube. Okay, let's do the math and see that the product volume produced will be 11.3 dm cube. Let's look at the first step in more details. Methane and water will produce carbon monoxide and 3 hydrogens, where it appears me to work out the enthalpy change via bond enthalpies. So we're going to work out the bond enthalpies of the reactants and products and apply the equation bond enthalpy delta H equals sum of bond enthalpies broken minus sum of bond enthalpies released. What's the logic? The logic is when you want to break bonds of the reactants, we'll need to input energy. Bond breakage requires energy, which will be positive enthalpy values. And we'll be forming new bonds, releasing energy, which will be represented as minus, which is why minus bond enthalpies of the products. So let us, we need to find what CH bond enthalpy is, where there will be 4 of CH single bonds. We'll be needing 2 of OH bonds. We'll be forming CO. Now this is quite tricky. I won't go into details, but it's going to be a triple bond. We'll need one of them, and we are already given the value for it, which is going to be positive 1077. Finally, we will be needing 3 of H2H singles. Let us go to data booklet and work these out. We need, firstly, H and H. Let's work backwards. 436. We will need 436. 436 times 3. Let's work out OH. OH 463. Oh, 463. 463 times 2. The final CH 414. Let's put these into the calculation. We want there to be bonds broken first. So 414 times 4 plus 463 times 2. Let's minus 1077 and also minus 436 times 2. Apologies, not going to be 2, but 3. Do the math, and we'll be given plus 197. Case expression is going to be the concentration of products over reactants, where our products are represented by carbon monoxide, 1 carbon monoxide, and 3 H2. So we'll be cubing H2 concentration over 1 methane and 1 water. 1 methane, 1 water, 1 carbon monoxide, and 3 hydrogens. State and explain the effect of increasing temperature on the value of Kc. Now, temperature is the only factor that affects Kc. Catalyst concentration does not change Kc value. Increasing temperature will be counteracted by decreasing temperature, which can be achieved by favoring the endothermic direction, which happens to be the forward reaction, as we have worked out the delta H to be positive value, which means forward reaction being favored will increase the position of will shift the position of equilibrium to the product side. More products, Kc value increases. Moving on, question 5 seems to be about organic chemistry, starting with ethene. Okay, ethene belongs to the homologous series. Alkene, easy giveaway question, where we're asked to name the next member of the alkene series. Again, a giveaway question. Propene is going to be the next member after ethene. Justify why ethene only has a single signal in its 1H NMR spectrum. Well, ethene is symmetrical, so that the double bond CH2 hydrogen environment is going to be identical for the carbon left and right. Symmetrical. Ethene has only one H environment. Next up is, what are the 2 possible products of incomplete combustion that is not found in complete combustion? So, are there sufficient oxygen to produce carbon dioxide? Or are there insufficient oxygen so that we'll only produce carbon monoxide or carbon soot, carbon solid? We'll be producing carbon monoxide gas and carbon soot solid. Ethene undergoes many organic reactions, one of which is polymerization, where ethene will react with another of itself, ethene plus ethene, in a continuous propagating manner to produce polyethene. And we refer to this as polymerization. We're moving on to kinetics question. Dinitrogen pentoxide. Dinitrogen pentoxide. Okay, must be a very complex molecule. Will turn into nitrogen dioxide and oxygen. And we need to measure the rate of reaction. What are the ways that we could measure the rate of this particular reaction? Well, we're given how the initial reactant is colorless compared to the colored product, nitrogen dioxide. That is brown. Color difference does exist, which means we could use colorimeter to measure how the brown color gets thicker and thicker and how fast. What else could we potentially use? Well, we are going to be producing gas, more gas, and therefore we could use gas syringe to measure change in volume. Measure change, color change. We're given the data for concentrations of the reactant, N2O5, and the corresponding rates. Multiple concentrations and rates. We'll probably be asked to draw a graph. Let's get ready to draw a graph, which is already partly drawn. All we have to do is introduce the best fit line. When we draw the best fit line, let us make sure we start at the naught origin. Why? Because no reactant, zero reaction rate. And also when we do so, let's make sure we pass through the points as much as possible. The reason why, I'm going to make sure that I pass through we've got how many points? We've got 4 points. I'm going to make sure the best fit line passes through at least 2 points. And if it does, there's 1 point above and 1 point below that best fit line, which is quite nicely drawn. Well, having drawn the line of best fit, it's clear that as the concentration of our reactant, nitrogen oxide, increases, the rate increases. And we refer to this relationship as positive correlation, directly proportional. So we would say N2O5 concentration is directly proportional to the rate. Directly proportional to reaction rate. Concentration is a factor that affects the rate of reaction. The way concentration affects the rate is going to be increasing substrate concentration, meaning collision frequency increase. Collision frequency will increase because there are more substrates, and collision frequency increasing will result in successful collision frequency increase as well.